Hassler here. I'm going to work through the 9.1 Explore and lesson. In class, I had students measure their hand span, and so of their dominant hand, and so they used centimeters. Using a ruler, they measured the distance from the tip of their thumb to the tip of their pinky of their fully stretched out hand, and then they recorded their hand span. And then I had them use that same hand to grab as many Starbursts out of a bag as possible. They have to grab the candies using their fingers pointing down, so there was no scooping. But it was like a claw machine. You hold the candies for 2 seconds before counting them, and then they recorded the number of candies that they grabbed. After counting, they put the candy back in the container, and then their group member did the same thing. Instead of recording data on the whiteboard, I just had them record. I recorded their data. I walked around and recorded their data. And then I posted this on the board so that they could put this into Desmos. And so I'll show you what that looks like. And so if you want to add a table, you just hit that plus symbol in the upper left corner. You choose table. And so I put this data in here. And after putting that data in there, you can see that we get a bunch of little dots that are graphed. And what you can do, once you create that table, if you want to see your dots, mine isn't down here because I already hit it, so I apologize. But down here, there will be a little magnifying glass. It says Zoom Fit when you hover over it. If you click on that, then you'll be able to see these dots. And some things that I noticed about these dots is that if I were to draw a line through these dots, something like this, it looks like my dots are increasing. I have this positive slope. In other words, and we put hand span, and we'll do this on the notes, but we put hand span on the x-axis, and we put number of candy or starburst on the y-axis. And so as the hand span increased, the number of candies grabbed increased. And this seems like a reasonable relationship. The larger your hand span, the more candies you can grab. And so what we did is we took this data and we transferred it to our paper. So we took these data points from the table, we put them onto our notes. And so we have that here. And first we had to label our axes. And so again, we said that the x-axis, this x-axis was hand span. There we go. Sorry, I'm not sure why that doesn't want to write. And we measured that in centimeters. And then we said that the y-axis was number of starbursts that were grabbed. Okay. And we just went ahead and labeled the x-axis. We went by ones. We started at 15. So I'm going to start right here at 15, which seems a little strange, but then we went by ones. So 16, 17, 18, 19, 20, and then 21, 22, 23, 24, 25. The largest hand span we had was up to 25. And so we started at 15. But because we started at 15 and not at 0, typically that origin is 0, 0, we made this little break in our graph, this little squiggly on the x-axis. That little break in the graph says, hey, I'm not starting at 0 and counting up to 15, that distance from 0 to 15 is not the same as the distance from 15 to 16. So it allows you to understand that you are skipping numbers on the x-axis. As far as the y-axis goes, we ranged anywhere from 5 all the way up to 30. And so we just went by 5s, and we did 5, 10, 15, 20, 25, 30. Okay. And then based on this scatter plot that we have here, we plotted our points. And so for sake of time, I'm just going to go ahead and plot some of the points that we had. There we go. And we said that this looks like it has a positive, somewhat linear association. Not quite exactly, but close. take a couple of these away. There we go. And so it says describe the relationship in the scatter plot. So we can do a couple of things. We can say as hand span increases, the number of candies grabbed increases. Another thing that we can say is this shows a positive linear relationship. And so I can use Desmos to help me find what is called the line of best fit or the regression line. And a line of best fit is going to be the line that goes through the data in the same direction as the data, so that about half that data is above and half that data is below. And I want Desmos to calculate for me exactly what that perfect line of best fit would be. So we're going to do this in Desmos by typing the y equals mx plus b formula. But we're going to use y1 and x1 since that's what our data has. And so we can just add that right in this next box down here. We're going to say y1, and if you type in 1 right after y, it'll automatically do a subscript. We don't want to say equals. We want to do that little squiggly equal sign. So you have to hit shift, and then above the tab key or right next to the 1 is that little squiggly symbol. And we want to say m for slope, x1, because we want the x values in my table, and then plus b. And so let's see. I'm going to erase my line of best fit here. And so, that's because I have x1 and x2. My apologies. My table up here says x1 or x2 and y2. So I'm going to change it to say y1 and, x1 and y1. There we go. That way when I go to write this equation, I have the information that I need. So notice down here in parameters, it says m equals, so that's my slope, 1.34. My y-intercept is the b, so negative 10.48. And so going back, I would have y equals 1.34 x minus whatever that y-intercept was, 10.48. And we're going to sketch this line of best fit. So again, notice that I have this green line now graphed, and I have about half of the data points above this line and about half of them below. We can double check by counting. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So pretty close. If you would count this one above or below, it looks like it's mostly on the line. And I'm moving in the same direction as this data. Okay, and so I want to draw a line of best fit on my page that would mimic this. And so I want to make sure that I'm going through my data, so about half is above and half is below, and that I'm moving in the direction of that data. I feel like I could have done a better job of drawing in that line. I might have drawn it up a little bit more like that. That looks a little bit better. And it says, what is the slope of this line? Interpret the slope in the context. And so my slope is the number being multiplied by x. Remember, slope is a ratio. Slope is change in y over change in x. And so I'm just going to put that reminder over here, change in y over change in x. And so I wrote 1.34 as 1.34 over 1. A reminder is that change in y is the number of candies. So we're going to say candy, 1.34 candy per. My x is hand span, and the unit on that is centimeters. In other words, you can grab 1.34 more candy for each 1 centimeter increase, this is all positive, so this is all an increase. I'm grabbing more, that's an increase. I have a bigger hand span, that's an increase for each 1 centimeter increase in hand span. Eight says, what's the y-intercept of this line and interpret? So the y-intercept is negative 10.48. But I like to write this as an ordered pair. So remember that the y-intercept always has an ordered pair of 0, comma, whatever that y-intercept is. And I'm going to label this, again, just like we labeled the slope up above. The x is centimeters, and the y is the candy. And so this would be saying that if your hand span is 0 centimeters, you grab negative 10.48 starbursts. And when we collect data, the y-intercept does not always make sense in the context of the data. It doesn't make sense to have a hand span of 0. It doesn't make sense that I could grab negative candies. And so this y-intercept in this case has no real meaning to it. Finally, it says LeBron James has a hand span of 23.5. Use your equation for the line of best fit. And so that's this equation right here. Use this equation to estimate the number of candies that LeBron would grab. So we've got y equals 1.34. And in place of x, we're going to put that 23.5 and then minus the 10.48. And so I have to go to my calculator and I have to type in exactly what I wrote. 1.34 times 23.5 minus 10.48. And it's about 21 candies. Okay. And so let's go ahead and take some quick notes on what we just discussed. All right. And so there are two things that we took a look at today. We took a look at scatter plots, and then we took a look at line of best fit. I'm going to split this box into two. Scatter plot and line of best fit. Okay. So a scatter plot is a graph that is created using data. The x-axis is the independent variable. This is something that I know you guys have talked about in science class. And the y-axis is the dependent variable. And a scatter plot can just be, a bunch of dots that get graphed based off of a set of data. And we describe this based off of the direction and the form. So we'll say, hey, this has either a positive or negative direction. And then we'll say things like, that's form, F-O-R-M. We'll say things like linear or nonlinear. If there's no curve to it, then it would be linear. But if it has a bit of a curve, it would be considered nonlinear. So it could be a U shape like quadratics, or have a curve like an exponential function, okay? The other thing that we talked about was a line of best fit, and that line of best fit is in that form y equals mx plus b, where we have a slope and a y-intercept. And in order to draw a line of best fit, we have to go through that data. So go through, I'm going to say middle of data. So we have about half above and below. And the other thing is that we want to move in the direction of the data. Okay, so your job then is to work through these couple of examples. It talks about the end of semester math teacher wonders if a student's attendance has an impact on their final exam scores. And so you're going to use this graph that is already graphed for you. It already has a line of best fit for you to answer some questions. And that is your homework. So if you have questions, let me know.